All right. So, sometimes when I ask you some question, ask people some question, I typically don't see evidence. I just hear that, oh, I guess I just feel like. And today we are going to see there are also situations when the processors would do things when the processors just feel like that this is the right thing to do. But before we talk about that, let's put us back from where we are coming from. So regarding pipelining processor, I think everyone, if you have passed your undergrad computer architecture, you should already get a feeling that pipelining is an idea where we partition the execution of an instruction into different stages. And the benefit of doing that is that in the way that your processor, each time you only need to advance an instruction from one stage to another. And what does that mean to you is that the same resource, you can free it up for other instructions, so you can execute multiple instructions at the same time. So for example, like at this moment, 4 instructions, they are all in different places in the processor. So you can fully utilize the precious circuit space that you have. And that's one benefit. And the other thing is that if you can continuously fetching instruction and finishing instructions, then you are basically achieve the same CPI as conventional processors. However, that's the ideal situation. Most of the time, we are not going to reaching that. We are not going to reach that ideal world. Instead, we have hazards. And there are 3 types of hazards. Structural hazard, meaning that 2 instructions, they may be considering like competing the same hardware resource. Control hazard, meaning the case where the processor doesn't know what to do next. And turns out that we have to disable the fetch for a while until we figure out what's the next instruction to fetch. Or the data hazard, that we don't want to execute some instructions. However, unfortunately, the right value that we want to look for, they are actually still being generated or somewhere in the pipeline that's not being able to propagate to my instruction resource first. So then turns out that we have the data hazard. So we have been talking about to address the structural hazard. There's no other ways better than redesigning the hardware. So in the last lecture, we talked about write first, read later research file design. And then we talk about split L1 cache to address the competing issue between instruction fetch and data access stage. And there's one more thing that if you could remind yourself about is the non-blocking multi-bank cache design. It's actually helping to pipeline multiple memory instructions at the same time. So those are all the hardware design that is now almost by default in every processor to deal with those pipeline hazards. So then we talk about control hazard. And a control hazard coming from the situation where we where we meet a branch. And for a branch, we would have two results. One is taken or not taken. The other is not taken. By taken, it means we are simply moving the direction to any other place rather than my next instruction. And by not taken, it means that the upcoming instruction should be my next instruction. So it has no correlation with the truth or false in this statement. It's more about if you are going to change the direction or not. So for this kind of a situation, typically the right thing to do to tell if the relationship between your statement and the branch is you have to go into your assembly language to see what's going on. But as I said, this class is by no means a class that wants you to really be an expert in assembly language, although you do need to figure out the assembly language in some perspective. For example, one of the common fallacies that I see from your midterm is that a lot of people, they think what really defines a loop is a label and a branch instruction, yes or no, right? You have to pay attention. It has to be jumped back to the same level, right? Label, right? So for example, here in the very beginning, we have L12. So the complete loop is actually somewhere starting from L12 and then jump back to L12. So actually the whole thing is a loop, right? And one of the common problems that I see, a lot of people, they see a label here, they are exciting, and they think, I found a loop. But turns out that's how you miscalculated the number of instructions within a loop iteration, right? So if you could have remembered, the right answer for each loop should be somewhere around like 11 to 13 instructions in the midterm. If you don't have that impression, that's an obviously sign that you fall into the problem that you misunderstand what really a loop is, right? But for that kind of stuff, that's what I want you to know, right? Because knowing where the loop boundary is actually important, right? So so here's the thing, right? So first of all, but from this, at least you know, like, what is a branch instruction, what defines a loop, right? And there are branch instruction, and it's not necessary if the statement is true, you will have taken or not taken, right? So those are stuff that you should have figured out. And then, but why do we care about the control hazard? Because if you think about the problem with control hazard is that whenever you meet a control hazard, you cannot continuously fetch instructions, and no input, you won't have output. So even though I want to redesign my house, if I have perfect backend that can continuously execute the instruction, even though if I solve all other hazards, make all instructions that can execute perfectly in one after another. However, if you cannot continuously feed the instructions, then you are going to have a gap anyway, right? So that's not good. So that's why we think we should do something to mitigate that gap. And that answer is that we have branch protection. And today we are going to talk about how processors predict the outcome of branch. However, before we talk about that, let's talk about this, since you have taken midterm. And I think you must have done some degree of this, right? Like, when and how will you make a guess? All right, I can hear people are discussing what happened during your midterm. So, what's your name again? Yeah, Siobhan. Do you want to tell us about what happened during your midterm when you make a guess? And why do you think it's okay to make a guess?
On the multiple choice, there's only like 2 that I guessed on. And I think I got both of them wrong. The other ones I didn't guess on and I got right.
Oh, you didn't guess it and you got it right, so don't guess. Anyway.
But it was just like, I didn't remember.
But what do you think? Like, what do you feel about like when you guess it wrong?
Like, it just guess something that makes sense. Like, you know.
Yeah, but like when you see it's wrong, what do you feel?
Not good.
Not good, but is it bad? Is it really bad? Is it worse than doing nothing?
No.
No, right, okay. So one policy first, right? When you want to make a guess, right? It's typically because I know making hunch won't hurt, right? Okay, then how do you guess?
Eliminate some. If you know that some are wrong, eliminate them, and then from the rest you pick whatever feels right.
Okay, but what if you really don't know at all, right? Like that's my feeling when I took my GRE.
Whichever letter you pick the least.
Whichever letter you pick the list, right? So some kind of a history based, right? What else? What else do you guys have in mind? Like, how do you make a wise guess?
If 2 guesses are similar.
If 2 guesses are similar?
Then it might be trying to trick you and then one of the 2 is correct.
One of the 2 is correct. Okay, what else? So some correlation. Okay, that's a good one. What else? Come on, be honest. You must make a guess, right? You must make some guess, right? What's that?
Something which has the most keywords as the question.
Most keywords, so something that appears the most often. Okay, that's a good approach. What else?
Some of my professors use definitive language, like always or guaranteed.
Okay, some language that looks like, you know, there's nothing 100%. Right, so you know, like whenever we say something 100%, that must be wrong. Okay, that's a good one. I will try to have some question like that, and it's not intuitive in that way. But you're right. It's typically difficult to make a bold statement saying always. Right. Sometimes I'm thinking about, is it always true that 1 + 1 must be 2? Haven't you ever thought about that? No, I know, right? But anyway, okay, so, but those are good discussions. Today, we are going to talk about dynamic branch predictions, and we are going to talk about several different branch predictors, and they span quite a lot different spectrums regarding how can we make a wise guess regarding how our program is going, what our program is going to do. So let's start with the basic concept of a branch predictor. So the very last question that I asked in the last lecture is that for each branch, what we are expecting to see from a branch is that, is it taken or not taken? And if it's taken, where are we going? So it turns out if we want to make a branch predictor, here is the most useful output that the branch predictor should provide to your processor. First, is the branch going to take or not take? And the second thing, if it's taken, what's the right program counter, instruction pointer that I should direct the processor to? So here is what we would expect, right? So first of all, to record. So regarding the branch target, which is the PC we are going to use when the branch is taken, it's always encoded in a format as an offset in the machine code. So what does that mean is that to get the right target PC is the current program counter plus that offset from the branch itself. So what's encoded there is always an offset. You might wonder why we always encode branch as using offset instead of absolute program counter. And the answer is, if you think about the nature of a program, when you compile your program, the relative location of instructions within the same function, within the same object file, the same executable, is a fixed distance. When you compile, that's always a fixed distance. But there is also a dynamic factor there. For example, when you call an external library, like standard library from like a C++ library, you would perform something called dynamic linking for those library objects. And why are we doing this? There are two reasons. First, you can make your binary size smaller. So if you compile one executable, it's only the code that belongs to the creative that you have in this particular program rather than those other libraries. So condense the size of your executable to save space. And the other thing, which is probably more important, you know that the library, they are always evolving. For example, like CUDA libraries, they change from one version to another, which is annoying all the time. I know, and I suffer from that. But most of the time, if it's a well-defined library function interface like C libraries, to be honest, you don't feel any difference, but each different version of the C standard library, they have slight difference in their implementation. And if you use dynamic linkage, it would help you to get benefit of the updated version of the library. So what is that? But if you think about the code would be the library code will change all the time. Every time when you load it, you may start with a different starting location of your functions. So that's why we cannot use absolute addressing, because every time the operating system will load your library functions, your code into a location that is not always the same. So it always has to be the case when we start running the program, we would know where this function is placed in a virtual address space. Then that's the time we are going to know our PC for sure. However, after you start running it, the PC will never change. So what does that mean is that once I run into this branch one time, once the branch target address is generated one time in one run, for the whole run, this branch target PC is going to be the same all the time. So the first thing that we do to address the issue that we need to predict what's the taken address is we have a branch target buffer which records the taken address of previously visited branch instructions. So that's one thing. So it's pretty much like a cheat sheet of all the previously generated branch target PC. And then the other thing that we attached to each branch instruction here is the state. And the state is used for us to predict if I see this branch instruction in the future, should I predict it to be taken or not taken? So this is the design of a basic branch predictor. So as you can see, whenever I fetch an instruction, I check the PC to see if this is a branch. And if this is a branch, then I am preparing the target PC as another input of a mux to my program counter. And if the state telling me that I should predict taken, then I would take that predicted PC. However, in the meantime, how do I make a better prediction? As many of you said, right, based on what previously appeared, I would change my mind in the future, right? So you also need to get the feedback from the real execution result of the branch node the next time if I see this one, if it's taken or not taken. And the other purpose is that if I have an inconsistency between my guessing result and the branch outcome, I know I have to do something to flush those incorrectly fetched instructions and put the program counter in the right direction, right? So this is basically why the branch prediction is designed in this way. So the very first branch predictor that I'm going to introduce is basically based on the hardware that I introduced here. Is called a two-local bimodal local predictor. And there are several terms here. Each term has its own meaning. So first of all, let's go from the end. It's a local predictor. So in branch prediction, there are several categories. The first one is called local predictor. What does that mean by local predictor is that when I make a prediction, each branch has its own state, and the state is maintained and trained individually without any regard to other branch instructions. So that's a local predictor. And we have the bimodal and 2-bit. And let's look at the 2-bit. So the 2-bit means that I use 2 bits to maintain my states. And a bimodal means that I split out my state space into 2 sides, taken or not taken. So this design, a lot of people, they would try to memorize this state diagram that your textbook and a lot of other professors would teach you. But here's the way you should think about it. Forget about this guy. Forget about this whole thing. What really this 2-state is doing is a saturate counter. So thinking about how many numbers you can represent in 2 bits. 4, right? 0, 1, 2, 3. So what it basically says is that this is a saturate counter. Let's count from 0 to 3. How many previous visit to this branch is taken, right? So if it's 1, if the last branch is taken, then I increment it by 1. If the last branch is not taken, I decrement this counter by 1. Saturate means that if I reach 3, I stop incrementing. If I reach 0, I start decrementing. And with bimodal, it simply means if I am smaller than half, which is 1, predict not taken. If more than 2, equal to 2, predict taken. So do you need to memorize this guy? Not at all, right? I see a lot of other people, they are teaching students to play with this state diagram. I know they probably have a habit in like computational theory or like automata. But I'm not that guy, right? So I'm just teaching you, thinking about this. This is a saturate counter, right? So this is pretty much like your everyday life, right? Like saying that if I have a friend, right? You always have that kind of friend, right? They give you advice, right? Saying that yeah, don't worry about your midterm, right? Don't study this. I know this professor well. He won't test this, right? And the first time when you take the midterm, right, then you know that, well, he's not honest, right? The problem he say it won't appear, it shows up, right? Then you ask, and then the second time during the final, he told you that, oh well, this problem won't show up, right? And you trust him again, and then it turns out that problem shows up in the final as a big portion, right? And you fail the class. So now the next time when you take CS203 again, or take my class again, you know, okay, don't trust that guy, right? Because you have been fooled by twice, right? So this is pretty much the case that if the previous result and my current result is inconsistent for twice, then I would change my opinion, right? So let's do this, right? So let's run through it. So first of all, let me show you these pieces of code. This is a do while loop. And the reason why I'm doing do while loop, if you have paid attention to what I told you the last time, or you have paid attention to some of the compiler optimized code, you know that any for loop, they would translate that to do while loop in assembly language. So for a do while loop like this, right, you will see there is just one branch, which is the while, right? And that's assumed that currently we are putting our counter at the number 2. If you really like state machine model, then it's actually 1, 0, right? And right now I am doing the first iteration. And after the first iteration, because it's plus plus I, my current I value is equal to 1, right? So when I equal to 1, what's the current state inside that branch? What's the current state associated with that branch? What's the current state? 2, or say 1, 0, right? So if it's 2, predict taken or not taken? Taken, okay. Is the actual result of this one taken or not taken? Taken, right? So now, let's go to the case where we do another iteration, and at this time, because it's taken, so I know the taken direction should be right. So I increment my counter to 3, right? So now, for the next iteration, when I equal to 2, the current state should be 3. Predict taken or not taken? Taken. The actual outcome? Okay, so when I equal to 3, what's the state? 1, 1. Taken or not taken? Okay, right? So from 3 is equal to 1, 1. Predict taken. Actual outcome is taken, right? And because it's a saturated counter, so we are not going to increment the value of 1, 1 anymore. And we are going to continuously do the same until the 10th time, right? We predict taken, but because it's the end, right? So we are going to get it wrong, right? So now I'm having a 90% accuracy, right? Are you satisfied with a 90% accuracy? Yes? Okay. So, but based on that, right, can you, like based on your learning about a two-bit local predictor, can you somewhat look into this code and thinking about a case? If I have a just like a 2-bit predictor, what happened to these pieces of code? All right, let's take a look. So, okay, it looks like we need some discussion. So why don't you guys go ahead and discuss with others? All right, let's take a look. After discussion, okay, I love this answer. You know, that means that you guys really discussed. Okay, so can some of you tell me about like your experience of why you switch parties from one to another? Today is the election day. Right? Why do you switch? We shouldn't discuss, right? Like Proposition 50. What is that? I don't know about it, right? But how about this one? For those of you who already vote yes, why did you end up decided to vote no? Oh, no. Sorry, C and D, right?
Okay, well, my group is talking about how after sorting,
Mm-hmm.
your data is going to be consistently greater than or equal to threshold,
Mm-hmm.
like consecutively. So you're going to get a pretty good guess rate of around 100%.
Mm-hmm.
And then before that, if it's unsorted, it's either going to be above or below. So we figured, oh, that's a 50% chance.
Do you all agree with that? Right? So if you don't have data sorted, right, every data is pretty random. So if I want, even though I have the best predictor here, I cannot really guess the randomness there, right? So sometimes you think about a randomness is like, okay, this time taken, next time not taken. No, that's not random. The random is something that you cannot really predict, right? So if you have a almost perfect random function, to be honest, you cannot even make a guess, right? So the reason why I have the predictor starting with all zeros, it means that, okay, this predictor basically will stay at a certain direction, right? So you can assume this predictor will always predict not taken, right? So in this perspective, you are going to get it half of them right, right? So that's why we say 50%. But if you have data sorted, the only two places that you are going, well, the only two places you are going to guess wrong is the very beginning and in the middle when you switch the threshold, right? Other than that, it's monotonically increase. So you can pretty much know if the next one is going to be above or below the threshold. So you can make a perfect guess in that way, right? So that's why in our demo, with this sorting function, it will make your branch result a lot better. And in fact, as I mentioned, this is an implementation of a frequently used database query. So you can also imagine if today you are the database manager, the best practice to make your database outperforming is to find the most frequently queried column, make an index out of it, and also make your data sorted. And that would probably address 90% of the performance issues in database queries, right? So, but Now the problem that you might want to ask is that, okay, is that real, right? So now I'm going to show you the demo with performance counter information attached so you can really see what's going to be there. So this is the code, exactly the same as what I show you in a problem, and let's run it. So I'm going to run it for like 128K elements with 1,000 run. So it means that the number of queries I have is way smaller than the number of elements that I have. So it shouldn't be a factor that affect the complexity of the code. And then let's try to see what's the stats. So you can see if I don't sort it, which is a case where I have the sorted set as 0, the number of instructions is indeed smaller than the number of instructions that is necessary to perform the sorting. So sorting does increase the instruction count, right? So this is an overhead you paid. However, if you pay attention to the number of cycles, it's a 5-fold difference. And if you pay attention to the CPI, it goes down from 1 to 0.25. So it turns out you see a very significance in reduction of your execution time. And because you have to sort, so you do more data access. So you do see more significant number of data cache misses and data cache miss rate. However, at this point, the benefit of making the branch prediction correct, which you can see here, is I only have so previously I have 35 million branch misses, but now I only have less than 1 million of branch miss prediction. This is outweighing all the benefits of not having data sorted, right? So if you can see that, it tells us that, well, there is a very significant benefit of sorting your data in the very beginning, right? So, however, previously people don't teach you about that, or a lot of old-fashioned programmers, they don't do this, is because this requires you to have a branch prediction to be effective. If you are working on a processor without a branch predictor, this is not going to be effective, right? So this is a fact that with the architectural innovation called branch predictor, it's possible. But today, if you are running on a processor without branch predictor, which I don't recall anyone existing right now, but saying that you are working on a grandfather old processor, then this approach won't work. However, with modern processor, this approach is going to work, right? So another question that you might be curious about, why making the branch prediction correct can have such a significant drop of CPI, right? Previously, we see a very significant amount of CPI drop with better cache design or better cache aware code, right? So now, one thing I want to do is that I want to show you how expensive if we mispredict a branch or we don't predict. And we are going to reuse the same code that I show you. So the approach that we can think of is that I am going to compare the number of mispredictions and calculate the difference of cycles. So why am I doing this? It's because if you think about the difference among these two pieces of a code, there's basically nothing except for sorted or not sorted, right? So if you count so all the performance differences are mainly coming from the fact we have branch misprediction or not. So what I'm going to do here is that I'm going to use that to see how many cycles this mispredicted branch contribute on average, to let you see how expensive of that. So what we are going to do here is that I'm going to run another experiment so that we got a large number. Okay, we can run the same experiment as well. So like, okay, I'm going to run the same experiment again, and I'm getting this stats, which is pretty much the same as the last time. And then what I'm going to do here is that this is the number of branch misses. Oh, sorry, I'm going to run this. So I'm going to run it with more, so then we can see more comprehensive comparison. And this is the amount of branch misses that I have before without using sorting. And this is the amount of branch misses that I have with sorting. And then here is the difference in cycles. And then let's make a comparison. So with that, what do you say? Each mispredicted branch basically contribute around 34 cycles of latency. 34 cycle penalty for not predicting or misprediction. If you make it right, 1 cycle. If you made it wrong, 34, right? So what does that mean? Guessing it right really matters to performance, right? And 34 cycles, it's almost expensive as an L3 cache miss. An L2 cache miss, sorry. An L2 cache miss that you have to access L3, right? So you can see now why after talking about the cache misses, we are talking about branch, right? Because the average overhead is 34 cycles on the processors that I show you. But is a 2-bit local predictor good enough? So can you take a look of this more complex example and see if you are satisfied with this 2-bit local predictor? All right, let's take a look. So, oh wow, so this is definitely a good sign that I should put this question in the midterm final. But before I do that, shouldn't you guys discuss first?
I'm surprised it's not significantly lower. That's no exactly. That's what it don't.
All right, let's take a look of you. What do you guys think after discussion? Okay, C and E. So let's take a look. So when I equal to 0, right? Now I'm dealing with branch X because this is the very first branch that I'm meeting, right? And I said taken if I mod 2 is 0. So for this one, right now, is the actual outcome going to be taken or not taken? The actual is going to be taken, right? But what's the current state in there? 0, 0. So are we going to predict taken or not taken? Not taken. So this one is wrong. And after this one, we are going to move this counter to 0, 1, right? Because it's taken for one time. Now, after I'm done this, I'm going to meet this branch Y, right? So for this branch Y, I am meeting what state? 0, 0, right? Because we have a local predictor. So the state of branch X and Y, they are trend separately. So right now I'm at 0, 0. Predict taken or not taken? Not taken. Is the actual outcome taken or not taken? Taken. Now, when I'm equal to 1, and I'm going to branch X, what's the current state in there? 0, 1. Predict taken or not taken? Not taken. Is the actual outcome taken or not taken? Not taken, right? Because right now I mod to 2 equal to 1, which is not 0, so I'm predict not taken. So this time I get it right. So what am I going to do? I'm going to decrement the counter to 0, 0 when I meet the X next time. How about branch Y? What's the current state in there? 0, 1. Predict taken or not taken? Not taken. Is the actual outcome taken or not taken? Okay, so now if you complete the rest of the table, right? For the following, you know that for the branch X, I'm always going to have a 50% chance of guessing it wrong. And for the branch Y, I'm having 100%, almost 100% accuracy, right? And because we execute them evenly, what should be the accuracy? What is that? 75%, right? Okay? Okay, so are you satisfied with that? 75%? If your midterm is only 75, well, it's 75. Would you be happy with that? No? Okay, so we need to do better, right? But how can we do a better job? But before that, right? So first of all, the branch prediction, why we want the branch prediction is that we want to, we know that branch overhead is huge, and we need to have a better guess of the branch predictor. And the approach of dynamic branch prediction, we introduce the local predictor, but it only works out when you have a simple loop. If you have a more complex mix of statements, it doesn't really work out, right? So are we able to do a better job? So this week in the reading quizzes, you probably already read a lot of papers, and now we are going to start talking about these papers. So the very first paper is from Yopat's group regarding two-level global predictor. So here is what we have from the last slide. And we are not satisfied with our outcome of branch X. And it seems like for branch X, there is no good solution for that because it's kind of like random in a result. But if you pay attention, is it really that random? is it really that random? If you look at the actual outcome, is it really that random? What do you find? Okay, so you find there is a pattern that is always like 1 not taken followed by 3 takens, right? So here's the thing. If I forget about branch X and Y, just concentrate on this pattern, right? Which is pretty much like what you would do in a midterm. You don't do local guess most of the time. Sometimes you don't do local guess. You look at all the multiple choice result and you think, okay, it seems like I haven't got sufficient amount of C's. So I put a C, right? So this is pretty much like that, right? I found there is always a pattern in my result. So why don't I just fit in, try to capture that pattern and use that pattern as a way to predict, right? So this is the idea of global predictor. So the basic idea of a global predictor is that so far we know that we still need to keep track of all the branch targets. Otherwise, we have no way to predict the target PC, right? But now, instead of having states associated with each branch PC, I'm right now having states associated with my history. So here I'm demonstrating the case where I am tracking 3 bits of the history. And these 3 bits represent the last 4 execution result of my branch instructions, regardless which PC contribute to that result. So here you can see 0, 1, 0, 0 means the last 4 branch is actually not taken, taken, not taken, not taken. And for each of the branch instruction, for each of the branch history, I have a state which is pretty much the same as the way how we manipulate that 2-bit saturate counter associated with that state. It means that if right now you see a global history like indicated here, go to the corresponding index in the table to see for this particular pattern, should I predict taken or not taken? So that's, and then based on that, I make the branch prediction, right? So that's pretty much what we should be doing for this global predictor. So now let's run through this example one time, and you will get a better feeling regarding how it works. So first of all, right now we are at a case of I equal to 0 at branch X. So right now, because there was no previous result, so we assume the GHR is 0, 0, 0. And to save our time, I just make 3 bits of the GHR so that we don't have that many entries to track down. So for GHR 0, 0, because it's the first one, so right now let's assume everything is 0, 0. So are we predict taken or not taken? Are we predict taken or not taken? Not taken. Is the actual outcome taken or not taken? Taken or not taken? Taken. Okay. I equal to 1, branch instruction 1. What's the current GHR? 0, 0, 1, right? Why we have a 1? Because the last actual outcome is a taken, right? What's the current state within there? 0, 0. Predict taken or not taken? Is the actual outcome taken or not taken? Taken. Now, when I equal to 1 again, when I meet branch X, what's the current GHR? 0, 1, 1. Because the last 2, they are taken. Right? So it's 0, 1, 1. And have we seen this pattern before? No, right? So that's why the state should be 0, 0, because that's the first time seeing it. Is the state taken or not taken? Taken or not taken? Not taken. Is the actual outcome taken or not taken? Not taken. Okay, so we got it right, but you all know this is just by coincidence, right? Now, when I equal to 2, when I meet branch Y, what's the current history? 110. Have we seen this pattern before? No. So what's the state in there? What's the prediction? Is the actual outcome taken or not taken? Taken. When I equal to 2, branch X, what's the current GHR? 101. What's the state in there? 00. Taken or not taken? Not taken. Actual outcome? Taken. Now, when I equal to 3, the current branch is Y. What's the GHR? 011. Have we seen 011 before? What was the state in there? 00, because it was predicting not taken, but actually it's also not taken, right? So we are predicting not taken, but the actual outcome, taken or not taken? Taken or not taken? Taken. So far, they only get once right, right? This is actually my feeling every time when I answer your question. I was trying to teach you. I try to see, and then every time when the problem has slight difference, you guys still get it wrong, right? And what can I do? Be patient. So if you want me to be patient with you, you should be patient with that too. Okay, so let's keep running it. I equal to 3, branch X. What's the current history in there? 111. What's the current state associated with that? 00. What's the prediction? Not taken. What's the actual outcome? Not taken, right? So this is just lucky, right? But let's keep going. For this, I equal to 4. Branch Y. What's the current history? 110. Have we seen 110 before? Yeah, so what's the current state inside there? 01, right? Because the last time it was here, so it's not taken become taken, right? So we are incrementing that by 1. But this time we are still predicting not taken, right? But the actual outcome is taken. But you know the next time, if you see that pattern, it's going to change its prediction. You see some hope, right? That's my feeling about the office hour. After several iterations, okay, I see some hope. I feel like I can continue. So continue. I equal to 4, branch of X. What's the current GHR? 101. Have we seen 101 somewhere? Yes, so what should be the right 01? Predicting taken or not taken? Not taken. Actual outcome? Taken. Okay, so we still get it wrong. But you know, something is starting to make a difference, right? So just give it some time, right? So now, when I equal to 5, branch X or branch Y, what's the current state in there? What's the current GHR? 011. Have we seen that before? Yes, right? So what should be the current state in there? 01, predict taken or not taken? Not taken, but the actual outcome? Taken. Still not working. Come on, I'm not going to give it more time. Be patient, okay? Now, when I go to 5, X, what's the current state? What's the current GHR? 111. What's the current state in there? 00. Okay. What should be the prediction? Not taken. What's the actual outcome? Not taken. Okay. Okay. Seems like it's doing something. When I equal to 6, for branch Y, what's the current GHR? 110. Have we seen that 110 before? What should be the state in there? 10. Predict taken or not taken? Taken. Actual outcome? Yeah. The Don't you see that? Right? Now, when I equal to 6, branch X, what's the current GHR? 101. What's the state in there? 10, because the last time is 01, and because it was taken, right? So it should be 10, right? We predict taken. The actual taken. Now, when I go to I equal to 7, branch Y, what's the current GHR in there? 011. Have we seen that before? Yes. So what should be the state inside there? 10. Predict taken or not taken? Taken. What should be the outcome? Taken. Now the next one. When I say branch X, what's the current history? 111. What's the state in there? 00. Predict taken or not taken? Not taken. The actual outcome? Okay, now when I equal to 8, I mean branch Y, what's the actual outcome? Oh, sorry, what's the GHR? 110. Have we seen that before? Here, right? So what should it state right now? 11, right? Because it was 10, but I incremented by 1, right? So 1, right? Predict taken or not taken? Taken. Actual outcome? Okay, so if you keep going through, you will know, okay, for the rest of the iterations, right, I am predicting almost 100% correct, right? So now I'm asking you this question. If I have 2 predictors, which one would be the better for different situations? All right, let's take a look. Okay, so most of you pick C, but why don't you compare with others? Like, what are the 2 that you have in mind? All right, let's take a look. Okay, after discussion, okay, most of you think the answer is C. So let's take a look. For the first one, is the global better than local? Yeah? Why do you think so? Why do you think so? There is a pattern, but how long is that pattern? How many bits do we have? 4. If you only have 4 bits, are you going to capture a 10-bit pattern? And if you consider we have 2 branches, right, it's actually 20 rather than 10. Is it going to capture that? Right, so I would say about the same, because they are always able to capture the outer loop, but for the inner one, there's always a 10% chance we are going to guess it wrong for both. And in fact, if you consider the warm-up time that we need for the global is going to be slightly worse than local, right? So how about the second one? Who is better? It's about the same, but again, if you consider the warm-up effect, the local is probably better, right? How about the third? Global is better because there is a pattern, right? So this one, global, does a better job. How about the last one? About the same. That's what you think. I would say L is better, because thinking about that, right? The global predictor, you consider all other branches as well, right? So in fact, this one would be a noise that pollute the training of the predictor, right? So in fact, the local predictor, which train the branch state separately, would do a better job. So for this question, the majority is wrong. And that's why sometimes I want you to discuss, because if I want you to discuss, it's because I know the answer, I know you are not right, right? But here's the takeaway, right? We have local predictor and global predictor. Global does address some of the benefits, but it's not but none of them is perfect. So we have the third, hybrid predictor. So the first hybrid predictor I'm going to talk about is a tournament predictor. So what is a tournament predictor? Is that above the local and global predictor, it built another level of predictor called predictor. So what the concept of predictor is that it's a predictor that predicts which predictor is going to make a better prediction. So here is how it does in hardware. We have a branch target buffer. We do see the state, but the state here is not used for branch prediction directly. It's used for predicting which predictor will have a better prediction. So saying that if 1 is the local predictor or 0 is the global predictor, which I don't quite remember what I do. But here is the thing, right? So for example, I still have global and local predictor, but here I am using a predictor to predict either the global or the local would make a better prediction, right? So here, I'm basically doing this. The update of the state is based on which predictor gets the right result of the last time. And to simplify the explanation, I'm only using like 1 bit. But in fact, if you want to make a more solid predictor, you probably need like 2 bit or even more, because this is like, okay, now I have 2 friends, right? I want to know like which friend always give me a better advice, right? So if this friend always get right the last time, I trust this friend the next time, right? But if it gets wrong, then I would try another friend the next time. This is the philosophy of using 1 bit, right? But for 2 bits, it's more about like, okay, if I have the friend getting wrong twice, then I would trust another, right? So this is the idea of tournament predictor. So it's not a global predictor. It's also not a local predictor. It's a hybrid predictor because based on the prediction from the predictor, it makes the prediction, right? So here is the concept. So both of the predictor, they would make a prediction, but you have another level to try to give a confidence level for different predictors. Basically, that's the idea, right? So that's one way of making a hybrid predictor. And another hybrid predictor that is also pretty popular is called a G-share predictor. So the idea of a G-share predictor is it's still a global predictor as its base. However, a problem that we see from the very last example of the last reading quiz question is that there might be some branch that pollute my result. So it gives a hash to the access of this branch target buffer in a state in a way that when I am accessing this, I am exclusive or the current global history with my branch PC as a method to de-alias history for each different branch instruction in some sense, right? So in this way, it's still a global based. However, even though the same history, they will end up mapped to different entries in the state table because I'm trying to make an exclusive OR with its own PC. So if it's a branch that's highly polluted by other branch, if you have this approach, then it will make sure that it will have its own status trend locally, right? So this is also considered as a hybrid predictor because it's not completely predicting based on the global history. So that's another predictor. Now, for the times perspective, some of the predictor I can talk about the next time, but there's another predictor I think is easier to understand called perceptron. So perceptron is a branch predictor that's published in 2001. So a lot of you might think about, well, neural network is something new. But if you look at this paper, it's more than 20 years ago, right? Long time ago, computer architects already thinking about how to solve computer architecture problem with neural networks, right? So this is also a class. So branch prediction is actually one of the most early application of machine learning. And why? Because branch prediction essentially is a machine learning problem, right? So you learn how to predict conditional branch, right? And the input of the predictor is basically your history and a set of branches, right? And then the idea of using neural net, well, because it's already like a machine learning problem, right? And you want to predict taken or not taken, it's like a 2-class classification problem, right? So any method that you can think of that can be used for 2-class classification is basically a good method that you can use for branch prediction, right? And based on what you want to gather from the program execution, they are different, I would say like properties, parameters that you want to fit into this branch predictor. But the basic idea of perceptron is we use a set of like history, and for each PC, how are you going to use this history together with a weight function to generate our prediction result? So here's the concept. Depending on how long the history you want, right? Each history serves as an input parameter. So for example, if I say I have 10-bit history, this 10-bit history would be an input vector. And for each of the value, they would multiply with a weight. And how to adjust the weight? You can use backpropagation. You can use whatever circuit that you think is reasonable to adjust the weight, right? So you should adjust the weight based on the actual outcome. But when you make an inference, make a prediction, the basic idea is that gather each bit of information and make a prediction based on this linear function, right? So that's the basic idea. And here's the training algorithm. But here is what I'm going to show you is that the basic idea is you make a prediction based on the trend weight vector associated with each branch. So as you can see, the weight vector is per branch basis. So this is actually local. However, the history that I'm using to predict is a global history. So there is some flavor of global, right? But if you think about why is it like a hybrid predictor, you can imagine if this is a branch that local is vector, local prediction is better. Theoretically, a good machine learning model should only give weights to the branch outcome that is associated with this particular branch. Then this is pretty much like a local predictor, right? But if other branch are more useful for prediction, then give higher weights to them. Then this is pretty much a global predictor. So that's why perceptron, we also call this is a hybrid predictor. And regarding how we operate on the perceptron and like some of the design decisions that we made in modern processors in dealing with branch prediction, we will leave it to the next lecture. And here are some things that I want to let you know before you leave the classroom. So first of all, next Tuesday, because it's Veterans Day, I'm surprised that they picked Tuesday as the day off. So we won't have lecture next Tuesday. So the next reading quiz we'll do next Thursday instead of Tuesday. And we have programming assignment 2 due this Thursday. Assignment 4 is already released and due on November 20th. And you might, although we do have a lot of assignments, but don't forget, every time we give this assignment way earlier than its due date. And if you pay attention to the way how we design this assignment, they are a self-contained document in a way that even though you were not in my lecture, even though like you just read the assignment itself, it's good enough for you to finish that assignment if you read those statements carefully, right? So it means that you can start as early as you want. And another thing, a lot of people have been asking me, which I never understand why people care about this, but the midterm average is 67, maximum is 92. I don't know how that would help you because knowing the average, how does that help you? I don't understand. But anyway, what really affects your final grading is everything, not just the midterm. Midterm is only 20%. So one thing I do encourage you, if you really wonder, where am I in a class, right? Go to this My Grades, which give you the overview of how many points that I received so far. That includes not just your midterm, but also your reading quiz and assignments. And based on the projection that I have, so first of all, a lot of people try to ask me about the grading policy, and I was going to tell you, like typically it's based on where is the gap among grades. So like this time when I look at this, like between these two guys, two person, I don't know who they are, there is a significant gap between them and the rest of the group. That's how I separate A plus from A in these cases, right? So this would change. It doesn't mean that at the end there's only 2 receiving these A pluses. Like last year, I have 5, right? So it's simply depending on how close you guys are, one after another. But one thing that I can tell you is that I am ranking everyone's grades and based on like where we see those gaps. And there is a good enough reason why I am separating students based on the significant gaps in their grades, because I hate people asking for better grades after I release the final grading. So one thing I typically would do is that I would make sure that when I separate you from A to another, it's a significant enough gap that unless you get more than 10 points in your final or whatever, it will change your grade, right? So what does that mean is that don't try to argue with me after the final grading is done, because it must be a case where we see a significant difference among groups of students. And as I promised you, if you take both midterm and final, you should get like B minus at least. But if you like just don't do the half of the job, which is your duty, then why should I pass you, right? So, but if you do everything that you need to do, I will pass you for sure, because as I said, I'm not someone who like to fail people. But if you really want to get better grades, right, and try to map yourself in this bar chart to see where you are, will give you a better idea if you are in a second half or the first half. All right? Other than that, enjoy the rest of your day. I will see you on Thursday.